Okay, good. That's going. So, oh, one other thing I wanted to show was the chat. So I can see it and also see who's in here today. Which I don't think you guys see it all anyway. All right, should be good to go. 2 days ago, when we introduced the idea of the electric force, we dealt with a few problems. For the first problem, we just considered the force on an electron a certain distance from a proton. And for a single charge, it was pretty easy to do. We just had that the force was equal to K Q1, Q2 divided by the distance between them squared. And then we had some kind of a unit vector that I'm just going to call R hat. And it pointed in the direction along the line between the two charges. So when we had the proton here and the electron here, and they're separated by a distance R, we might have written that down with R hat being a unit vector that pointed along that thing. And when the things are of opposite sign, this product will be negative, and so you'll be multiplying R hat by a negative thing, and the force will end up pointing in that direction because opposite charges attract. And I suspect the opposites attract, I don't know, it's almost, people use it to us or talk about it in romantic relationships often, but I think that expression probably either arose from electricity or magnetism. Could have been from either one. Okay, so that was the first problem we did. Then we looked at a situation where we had a couple of protons, a proton here and a proton there, and I may call this P1 and this P2. And we had a third proton down here that could be P3. And we looked at the electric force that was on this proton down here due to those two things. And in that case, we had that the total force would have been K Q1, Q3 over R13 squared. And I may not have used that notation. I don't remember how I happened to do it. Yeah, actually I did use something like that notation, but that would be along a line R13 hat, a unit vector that points in this direction. Plus, that was just due to that charge, there was also a KQ2, Q3 over R23 squared. And then that would be along the line R23 hat. And I didn't actually figure out these unit vectors, although I did figure out their directions. These things are just cosine things, sines and cosines, when you write them as a unit vector. So that was what we got for that. Now, if we had many charges, we might be able to come up with some kind of an expression that looked like a sum from I to however, or 1 to however many charges you happen to have, and you'd have a K times Q sub I times maybe Q, we could call the particle of interest Q naught in this case, and then we'd have an R sub I squared, which is the distance from Q naught to Q sub I, and we'd have to have a unit vector in here, some R sub I hat, and that would be a unit vector that points from wherever charge I happens to be to wherever charge 0 happens to be, something like that. And we'd have to add up over a bunch of those things. And we can go a step farther with this idea. So here's one charge or a pair of charges. Here are a pair of charges acting on one other charge, and here's a whole bunch of charges, n charges acting on one other charge. So we keep adding complications here. And then the next complication, I guess, is to consider a uniform charge distribution. And in that case, instead of having a sum, we actually would have an integral, and we did something like this. And we integrate over some uniform or some continuous charge distribution. And in that case, we'd have k times our little particle q naught, and then times some dq, which is going to be a little chunk of charge in a charge distribution. And for that one, you might have to add that over here. And maybe this is q naught sitting down here. And we'd have an r squared, which in this case would be the distance from this charge q sub 0 to some little chunk of charge in here. So maybe that's dq. And then, whoops, missed. Oh, well, should have planned that better. This would be r, but r is now a variable that changes continuously as you're going around this charge distribution. And let's see, and then we'd have an r hat, and r hat is another vector and another thing that's going to vary continuously as you're going around this charge distribution. So that's as complicated as it might get, a situation like that. We're not going to deal with any horribly complicated situations, but we are going to look at some today that are, well, we looked at one the other day that was a continuous charge distribution. That was one that could be treated one-dimensionally, but today we'll look at a couple of two-dimensional situations, and then there are some other ones done in the book. However, what we're going to do instead of considering the force every time is we're going to imagine, well, let's suppose one time we had some proton here, but maybe we wanted to stick an alpha particle there instead, or an electron, or maybe an oxygen nucleus or something like that. And we don't want to have to redo this entire calculation every time. And so what we do instead is we take this thing out of consideration, and we would take this out of consideration and this out of consideration, and we actually divide both sides by that. So we'd have the force per unit charge. In this case, it'd be F divided by that extra charge that we had out here. In this case, it'd be, well, I didn't draw a picture for this one, but in this case, it would be dividing by the Q3. And so we'll have force per unit charge. And what we're thinking about when we do that, in this case, we'd be doing some kind of an integral over the charge distribution. And we'd be calculating something at some point in space that's now empty. And so instead of having a Q naught sitting there, we'd just be calculating the electric field at some point P here in space, but we'd have an expression like this that we calculate. Oh, I said, use the word already. We'd be calculating the force per unit charge, where if we stuck a charge there, it would be experiencing a force. Now, we're going to be thinking that just the presence of the charge here does something to the space there, so that if we put a charge there, it'll be acted on. And this is something like dealing with gravity as well. We know that if we put a mass a certain distance away from the Earth, it's going to be experiencing a force and it'll accelerate toward the center of the Earth. That's what's going on with this that we're going to be dealing with. I think I just fixed the view a little bit here. So let's see what we can, oh, this we're going to call E, the electric field. And that's the idea of electric field. And this is introduced in sections 21.4 and 21.5. And they do a bunch of examples. I'm going to do some today. They do some different examples. And so you can check those things out. Now, units of the electric field. Force is measured in newtons. This is measured in coulombs. So the units will be our newtons per coulomb, at least for a little while. We're going to introduce a new concept in the next chapter or two. And I can't remember if it's the next chapter or the one after that. But there's an alternate unit for electric field, but I think we have to introduce electric potential first to get those other units. But this is good enough, newtons per coulomb. Now, that's the units of the electric field. If you think about the units of the acceleration due to gravity, remember weight was equal to mg. Well, if you solve this, weight is going to be measured in newtons. If you divide that by the mass, you can think of the gravitational acceleration as being the weight per unit mass at some point in space. This has units of newtons per kilogram. So it's a very similar idea to talking about the acceleration at some point in space. There it was newtons per kilogram, and if we wanted to know the actual force, we would take this thing and multiply it by the mass. If we want to know the actual force on a charge, we take this thing and multiply it by the charge. So once we know the electric field, we could imagine sticking an electron there, or a proton, or an alpha particle, or any charged particle, a muon or a pion or anything, and we'd find out the force that's acting on it. So that's the idea that we're going to be dealing with. This is one of the problems that I solved Monday, and we calculated the net force on P3 due to P1 and P2. And what I ended up with when I did that, let's see if I got, just use this. I found out that the force that was acting on 3 was equal to, let's see. Oh, the net force. I'll write that down here. It was 7.36 times 10 to the minus 12th newtons in the I hat direction minus 3.11 times 10 to the minus 11th newtons. That was minus 12. Okay, in the j hat direction. Okay, now object 3 happened to be a proton. I think they were all 3 protons. Yeah, all 3 of them were protons. If I divide that by the charge on a proton, F3 divided by just E, because that's the charge on a proton, I just take each of these numbers and divide it by all that stuff, 7.36 times 10 to the minus 12th newtons along I hat minus 3.11 times 10 to the minus 11th newtons along j hat. And I divide it by 1.60 times 10 to the minus 19th coulombs. And that'll give me the electric field at that point in space. And so say the electric field there, you have to do a calculation. This one's going to be pretty strong, but Whoops, missed a digit. Okay, hopefully I punched this in right. I'd have 4.60 times 10 to the 7th newtons per coulomb in the I hat direction, minus, and I'd have to do that other one. Okay, that one would be minus 1.94 times 10 to the 8th newtons per coulomb in the J hat direction. The electric field in the near vicinity of things like protons is quite high. This is actually if you had an electric field this strong in the air in a room, it would be strong enough to tear the electrons off of air particles, air molecules, and turn the air into a plasma. That's actually what happens during a lightning bolt, is the electric field is so strong it shreds the molecules of air and turns it into a plasma for a little time. Anyway, there's an electric field calculation. And now, if we wanted to, instead of that proton that we had sitting there in this figure, we could stick an electron there and figure out what the force is on it, or we could stick anything else, any other charged particle we wanted to. So that's what we can do with electric fields. Maybe sometimes it's kind of interesting to calculate them for individual particles, but I'm going to be doing some things with charge distributions here. So, oh, rats. Oh, I hate it. I just printed something and I had some text selected, so it only printed the selected text. And I wanted the whole works. Okay, well, we'll be able to do it here in a second. Maybe. Yeah, it's doing it. Okay, one thing that I'm going to do several times today is do an integration to determine something. And I have a series of steps that I'll do on those integrations. And it'll help you to learn how to do them, because we're diving in with stuff that I'm pretty sure you did not do when you were in your math class. So, let's see. I hope most of these came out expanded. Yeah, they did. Okay. I think we did. No, we didn't do this one the other day, but we had a particle sitting here and we calculated the force on it. This time we're going to calculate the electric field at that point P instead. And I don't know if you can read this one well enough or not. Somehow this didn't get blown up with the rest of them. Unless page 2 has that. No. Okay, this one's spread uniformly. Series of steps, determine the linear charge density of the rod. What we want to do is get the electric field there. So the situation is we have this charge spread uniformly along the insulator with a length L. So we want the charge density of the rod. Then we want an expression for the charge element dq on the rod in terms of an integration element. We're going to be integrating here, so the electric field will equal the integral of k dq over r squared in the r hat direction. And so dq will be some little tiny chunk of charge on some little tiny piece of that rod, and I want to have that expressed in terms of my actually linear charge density and my integration element dx. So that's something. By the way, this is an outgrowth of something that I didn't give you for electric fields. For a single particle, the electric field is going to be, oh, sometimes this is K sub E. I forget that. K sub E Q over R squared in the R hat direction, and R hat would be a unit vector pointing away from the charge. So that's for a single charge. If you've got a bunch of charges, the electric field will, whoops, there's not an arrow on that. That's supposed to be a sum. The electric field would be a sum over I to however many particles you have, and it would be K sub E Q sub I over R sub I squared and R sub I hat. And the R sub i's are different for every charge in the group that you have. This is the electric field at some point P. So, and then the R sub I hats are also different for every one of those. So this would be a situation where you might have Q1 here, Q2 here, Q3 here, and who knows, you might have a bunch more, but you're interested in the electric field over here at a point P. Well, the things you're going to have to consider are stuff like, here's R1. Okay, that's the distance from Q1 to point P, and then R1 hat would be a vector pointing in that direction, and it's a unit vector. And then similarly, let's see, I'll do it for Q2 because I think I can draw that one without getting in the way of anything I've already got. Oops, forgot to label something. This would be R2. That's the distance from charge Q2 to the point P. And this would be R2 hat, which is a unit vector pointing out from Q2 through P and pointing in that direction. And then you'd have something similar for Q3, but my drawing would get too messy if I did that. So that's how you could do it for a bunch of charges. And if you have a continuous charge distribution, it'll end up being an integral K sub E dq over R squared and R hat. And both R as a scalar and R hat are things that change continually as you're messing around or going over your entire charge distribution. So wherever it happens to be. So that's what we're going to be doing here. And we're starting with what's really a one-dimensional problem. It's like the one that we did yesterday. And I'm sorry that I didn't get this part blown up like it's supposed to be, but the rest of them are. Anyway, linear charge density. Well, it says it's uniform and a total charge Q is spread over a thin rod of length L so that lambda is just equal to Q over L, and it's a constant everywhere along the rod because it's uniformly spread along there. Well, that's pretty easy. Part 2 says to determine an expression for the charge element dq in terms of your integration element dx. Well, here's what I'll do. I'll just draw a little thin sliver of this thing and imagine that this thin sliver here has a length dx. And since this lambda is the charge per unit length, dq is going to equal lambda times dx. And I just kind of race past these things because I've done these problems so many times that I can keep track of that dq equaling lambda dx. But if you need to slow down and wrap your head around that, go ahead and do it. Now, I could represent lambda with Q over L, but it's just as easy since lambda is a constant. I'll just leave it alone for a while, and at the tail end, I might replace it with Q over L. So that's what we've got. Then it says determine an expression for the electric field element dE sub x in terms of the line element dx. Okay, well, dE sub x is going to be the electric field due to this thing. And something that I'll do here is I'm going to let this be my origin, and x is going to be measured from the origin out to wherever my little charge elements are. And when I do the integration, I'll integrate x going from 0 to L, the length of that thing. And I did this integral Monday, but it won't hurt to see it again. So the electric field due to that little chunk is going to be dE. dE sub x is going to equal, well, how far away is this point P from the origin? It's a distance L plus A, right? But how far away is point P from that little charge chunk there? Well, it'd be L plus A minus X. So that's something that'll be in there. Okay, so I'll have K sub E dq over L plus A minus X squared. And hopefully you understand that this length minus this length will equal this length here. All right, well, dq was lambda dx. So this dE sub x is actually equal to K sub E times lambda times dx and divided by L plus A minus X squared. Okay. What can I do now? I guess I can integrate. That was step 3. 4 is to perform the integration to find E sub x, and I'm probably going to do the same trick that I did the other day where I do a U substitution, but let's see what the electric field will equal. It'll equal the integral over this thing. I have to add up all the charge of K sub E lambda dx divided by L plus A minus X quantity squared. And my limits of integration, I'll have to integrate from 0 to capital L. So I hope that's, you're going to have to slide this up to make sure you can see the whole thing. I'm probably going to run out of room, which I usually do. But one thing I'll do here is since there's probably, you could look that up in an integral table somewhere, but I do my usual trick of a U substitution, and I'm going to let U equal L plus A minus X, then du will equal minus dx. So that's easy enough. I can replace dx with minus du. And this thing would just be u squared on the bottom. So that'll be easy enough. But I have to change my limits of integration. When x is 0, u will equal L plus A. And when x is equal to L, u will equal A minus X, I think. Yeah, no, it'll just equal A, excuse me. So my integral changes to something different. but I guess I could just write it here. Actually, I'll do this in 2 steps. The E sub x will then equal, replacing this, the 0 down here with L plus A, and replacing the L up here with A, and I'll have K sub E lambda dx is minus du, so I could put a minus sign in front of this thing and just put a du there. And then that's u squared, so I have u squared. So at least it's a simple integral now, like it was when I did this Monday. But what I'm going to do is, it's kind of, actually I could do it this way. I think I will. This is sort of integrating backwards. I'm going from L plus A to A, but that's okay. Should be legit. So my E sub x would equal minus K sub E lambda. And then when I integrate this, I get minus 1 over U. And I evaluate that at, let's see. Yeah, this is the order. Something like that. Well, a minus and a minus make a plus, so this E sub x will equal K sub E lambda, and then I've got just plain old 1 over U evaluated at these 2 points, which is going to be 1 over A minus 1 over L plus A. And I think that'll actually be positive because 1 over A is smaller than L plus A. So this will be a bigger value than that is, and that'll end up being positive. And you could do tricks on this, like I could get a common denominator if you want. A sub B times common denominator would be A times L plus A. So I'd have L plus A minus A divided by A times L plus A. And this just ends up being L on top. So K sub B lambda times L. You've probably done junk like this in calc, I'm guessing. Anyway, this would be the electric field at that point in space. And that's a fairly tidy expression for one as far as these things go. I'm not sure we could get any. Oh, and then finally you could replace lambda with, actually you could replace lambda with Q over L, and you'd end up with K sub E capital Q, that L's would divide out, times A times L plus A. So this is like, let's see, that's hard to see. Write it big here. It's sort of like the electric field of a point particle, which is actually K sub E Q over R squared, but we've got sort of a weird little geometric determination on it here. So this is sort of like an average distance. In fact, it is kind of, but that's the expression we end up with anyway. And so the fact that it's K sub E times a charge divided by a distance or a length squared, I know my units will be correct, so I hadn't followed that up. Okay, let's try another one to see how these things go. This one's similar, I guess, except now we have the charges spread non-uniformly along a rod of length L, and the dependence of the linear charge density on the position X is given below. It's actually equal to Bx, so that there is no charge right here at the left end, or the charge density is 0 here, but it increases linearly as we go along here. And by the time you get up to here, it's BL. And they say determine the constant B. Well, here's something that the total charge on that rod, and this is a bit of a leap. I'm just going to jump in here and do it, is going to be the integral of dq as you go along the charge or along the length of that thing. But dq is going to equal, for any little chunk of that thing, is going to equal whatever the charge density is there times dx, which is the length of some little chunk here. And before we were doing these integrals to figure out the electric field, I'm going to do these integrals to figure out what the charge or what the value of that weird little thing B happens to be. So here's a dx again, but now I'm just integrating over this to figure out, get the total charge. So let's see. So it would be the integral of lambda dx along that charge thing from 0 to L, and lambda is bx. So Q will equal the integral from 0 to capital L of bx, that's what lambda is, times dx. And I can handle an integral like that. It's actually b times the integral of x dx, which is 1/2 x squared, which I evaluate at 0 and L, which actually ends up being, well, at 0, it's 0. So it's BL squared over 2, I think, when I'm done with it. Now, the question was, what is B? If I solve that for B, I would get B is equal to 2Q over L squared. So kind of a weird thing in this case. But with that for B, my value of lambda ends up being, it's B times X, 2Q over L squared times X. I think when I'm integrating this and doing stuff along the way, I may just think of this as lambda equaling bx, so that I don't have to keep writing 2q over L squared, and I can save that until I'm done. Now, determine an expression for the charge dq associated with the length of the rod dx. Well, dq is equal to lambda dx. Try to get used to that idea. Oh, except soon we're going to be doing not just length charges density, but we'll start doing areas and volumes, but it'll still work for a while. That'll equal lambda dx, and lambda is 2q over L squared, or just bx. So I'll just go with bx dx, and we know that b is equal to 2q over L squared, so we can deal with that later. So there's an expression for dq associated with the length of the rod dx. But there's more to this problem. Next thing it says is determine an expression for the electric field element dE sub x at P that's produced by the charge dq. Maybe I'll just slide this thing down like this. I think you can still see most of that thing. Okay, well, I don't remember if they gave us a hint here, but I'm going to let x be measured from here again. So I will have a different integral than I had last time, but we'll just see how that happens to come out here. So there's x, and point P is at x equals L plus A. This is x, so the distance from P to that is again going to be A plus L minus x. So dE sub x will equal the charge on that little chunk, dq. Actually, it's k sub e dq. Oh, I used, well, that's okay. I can use a capital Q on there. K sub e dq divided by this distance squared. But dq is equal to bx dx. So I'll have k sub e times bx dx divided by a plus L minus x squared. So that's that. And I've got an expression for my electric field. So I'm working stepwise here through this. A lot of problems might just tell you to find the electric field E sub x at that point P. But by having this kind of guided solution, you can work through it stepwise, and it helps out when you're doing things like that, getting started on these. Okay, well, I need to integrate this expression to get it, and my total electric field will equal the integral as x goes from 0 to capital L of E sub x, which is that expression there, k sub e b x dx divided by a plus L minus x quantity squared. Okay, this is kind of messy, although you could probably look up this integral someplace. Let's see what happens if we do another u substitution on this thing. And so let's let u equal a plus L minus x. If we do that, one thing I'll get is that x is going to be equal a plus L minus u, because I've got an x sitting there like that. Something else I'll get is dx is equal to minus du. Is that part okay with you guys? I would think maybe at some point in calculus, you probably did things like this, u substitutions. So that's something we'd have. When x is equal to 0, u will equal a plus L again. And when x is equal to L, u will equal a again. So let's see what happens to this integral when I do all these substitutions. E sub x will equal something kind of scary here, but when x was 0, we'll have a plus L down here. And x is L, we'll have a up here. Let's see, because dx is equal to minus du, I'm going to put a minus sign in front of this thing and have a du at the tail end of it. I'll have that. And this is u squared on the bottom. But let's see, I'll have k sub e b, which I can pull outside the integral because it's a constant. And x was equal to a plus L minus u. Okay, this splits this into, or lets me split it into two integrals. And the first integral is just going to have, these are constants, so I can pull all this stuff outside the integral and I'll just have a du left inside. So this will equal, and this is, be careful on your algebra. I'll have minus k sub b times a plus L. So that's my first integral. And the integral from a plus L to a of du over u squared. So that's the first one. And the second one, I'll have a minus sign out front. I'll still have k sub b, and I'll have this multiplying a negative u there. The second one will be plus k sub b times the integral of u du over u squared. Well, that's an interesting one. You know what that becomes? That'll become du over u, which is going to be the natural log of u, and it's also a plus L to a. So let's do this first integral here. E sub x is going to equal, on the first one, minus k sub b times a plus L, and integrating that, I get minus 1 over u. Minus and minus is going to make this a plus, but I'm evaluating it at a plus L to a. So that's sort of like the one we had last time. And I'll go ahead and there's more to come on this thing. In fact, there's a plus thing there, but I'm going to evaluate this while I'm thinking about it. Minus and minus gives me a plus, so I'll have k sub b times a plus L. And then I'll have 1 over u evaluated at a and a plus L, so I'll have 1 over a minus 1 over a plus L, which I had last time, I think. So I've got this thing that looked similar to what I had before, and I still have that b floating around somewhere, whatever its value happened to be. Where did I put that? I don't know. But that's all right. We'll find it. Oh, let's take it down here. Yep, there it is. Okay, I want to not lose that. Okay, and then this integral here, there's a u and a up top and a u squared down, so that's du over u, which will integrate as, I've got k sub b as the natural log of u evaluated at a plus L and a, which will become k sub b. It'd be the natural log of a minus the natural log of a plus L, which is, when you have the difference of two natural logs, it's actually the natural log of a divided by a plus L. And so that's what this one happens to be. This is dimensionless. It actually has whatever the dimensions of k sub e times b here, and this actually is here too, because if you put an a sub L over each of these, this would be a length over a length and a length over a length. So in fact, That would be A sub L over A minus 1. Anyway, you could simplify it further. But then one thing I'd do along here pretty soon is to come back in and substitute B is equal to 2Q over L squared. And then it's just a bunch of algebraic substitution and simplification that you could do on here. But that's the main part of the problem. And kind of led you through it. Determine the constant B, get an expression for dq, determine an expression for the electric field element dE sub x, and you need to do it in terms of things that you can integrate for this problem. And so we got there. We have a decent solution there. Okay, I think, let's see, this one we have a charge Q spread uniformly along an insulator, which is a thin rod of length L, and you're to determine the electric field at point P, which is not on the axis of the rod. And so at least it's spread uniformly, so it won't be quite as bad as that last one. But for this problem, I don't know that I could get it done in 10 minutes, but I can start. And I do have a separate video where I've done this problem. It's up on YouTube and I can make a link to it. And so you can see how that one works. But let's just write down what we can so far. I want that electric field at P. In fact, I'm going to want a big drawing of this thing somehow. But yeah. Anyway, the linear charge density of the rod. Well, it's uniform. It's got a length L and a total charge Q. So in this case, lambda is just going to equal that total charge divided by the length of the rod. And every little chunk of the rod will have an amount of charge density on it, lambda times whatever the length of the little piece is. The next one asks, determine an expression for the charge element dq in terms of your integration element dx. So here we imagine again a little length of this thing that has a length dx, and dq is just going to equal lambda dx. So we're much of the way there. Now, what about the electric field down here at point P? This is going to be, let's see. Kind of interesting. Okay. We'd want to know the electric field down here due to this much charge, lambda dx, that happens to be up here. Well, something we're going to have to consider here is how far is it from point P over there to that? We've got a distance d up in this direction and then some distance here. Okay, well, I'm going to let this be my origin, where x is equal to 0 right there. And I'm going to have x go positive to the right and negative to the left. And so I could just say that this is a distance for a point x here. It'll be negative, but I don't care about that at first. And although I will have to consider that as I'm going along here. So the magnitude of the electric field here, due to that little bit of charge, is going to be dE sub x. It'll be K sub E dQ on that thing, divided by the distance from P up to this thing, squared. Okay, well, this is a right triangle here. Okay, and it's got a side D and a side X is actually what it's going to be. L is the total length of the thing. So don't think that this L refers to this distance here. Well, this length here will equal the square root of x squared plus d squared, little d squared. Okay, but it's the distance squared that we want, and that's going to be x squared plus little d squared is what it happens to be. Okay, so that's the expression for the electric field. And that's just the magnitude of the electric field. Oh, it says dE sub x in terms of the integration element dx. I'm not all the way there yet on this. So I'll draw a picture here. Yeah, this isn't dE. Well, this is dE. So here's our little dE there. And I'm going to use this for an angle theta. And because these two things are alternate interior angles, that's also theta up there. And dE sub x, oh, I'll put this up here. That's dE there. It's a vector pointing in that direction. And I made it nice and big so I can actually see my version. dE sub x would be this length here. Well, this length divided by dE will equal the sine of theta. And so dE sub x is actually this thing times the sine of theta. Okay, so now we've got another variable in here, which is kind of bad, theta. And that's going to be continually changing as we consider different things along this rod here. So how can I deal with that? Well, if I come back to this triangle here and look at it, blown up nicely, here's theta. This is x up here. And this is d right here. And this was the square root of x squared plus d squared. Okay, so far. Well, what's the sine of theta going to be? It's going to be the side opposite that divided by the hypotenuse. So this turns into k sub e dq over x squared plus d squared. And then that sine of theta is x divided by the square root of x squared plus d squared. Now, I have to back up here and think. If this charge is positive up here, that electric field down here will be pointing in that direction. Its x component will be positive. Okay, as long as x is squared, I don't have any problems. But this x is not squared. And so on this side, it's going to be negative. That means my dE sub x would be negative. And so I need to put a minus sign in front of this expression to get my electric field pointing in the direction that it has to be doing. And so that's something that I have to back up or pause at this moment and make sure I get it pointing in the right direction. All right, well, I can simplify this expression, and that's as far as I'm going to go with this right now. Although, actually, I could probably get the dE sub y as well. But the dE sub x, if I simplify this thing a little bit, I'd have minus k sub e. Let's see, I can put the x in front of that. Oh, dq was lambda dx. So I'll have x lambda dx for my numerator. And on the bottom, This is x squared plus d squared. If I imagine wrapping it in parentheses, it'd be the first power. This is x squared plus d squared to the 1/2 power. On the bottom, I'll actually have x squared plus d squared to the 3/2 power. And so that's something that I'll have to need to find an integral for integrating x dx over x squared plus d squared to the 3/2 power in order to solve that, which should be doable. Now, let's get the dE sub y. dE sub y is going to equal dE times, let's see, where was I? Okay, here's dE. dE sub y is going to be the part that's pointing down here. That's going to be dE times the cosine of theta. So I can simplify that. Let's see, dE was k sub e dq over x squared plus d squared. The sine of theta, no, cosine of theta, come back to this triangle. That'll be the adjacent side divided by the hypotenuse. That's going to be d over the square root of x squared plus d squared. So d over square root of x squared plus d squared. And that'll be okay. It's going to be pointing downward. So if I used my usual coordinate system that had y pointing up, I'd have to put a minus sign on this. So I'm just going to let x point that way positive with its origin there, and I'm going to let y point down. And then there's nothing wrong with this expression. It's just fine. And that's dE sub y. And I can simplify it a little bit more with writing this as lambda dx. And that would give me k sub e, this is dE sub y. I have a d and a lambda, and this d is a distance, it's not a dq. D times lambda and times dx. And my denominator is the same as the other one. This will be x squared plus d squared to the 3/2 power. Now, may seem weird that we have the little chunk of the electric field in the y direction depending on x, but it does. And to do the integration, I'll have to integrate this thing from 0 to L, or from actually minus x2 to x1 is the limits of integrations, and both of these. So my e sub x will take the x expression and integrate it from minus x2 up to x1, and then dE sub x. And e sub y is going to be something similar. It'll be minus x2 to x1 of dE sub y. And I'm going to stop there. We're long enough. But on the other video, I finished that off. And then we also consider the expression as x1 and x2 get very long. In other words, as they go to infinity. And so we can deal with that later. But check out the continuation of that. Okay, that was a few challenging problems for integrating the electric field. And tomorrow we're going to be looking at the motion of charged particles in electric fields. And your book, I don't know why, but they don't really cover that topic. And so I've got something that I made a PDF out of another textbook that does have a nice coverage of it. And also, I think the open source or the OpenStax book has a unit on that as well. So you might be able to look at that, and I'll provide a link to that so you can see it too. Anyway, we'll stop here. And where do I stop the recording? There we go.